Okay, good morning, everyone. Sorry for the delayed start. For some reason, my screen mirroring is not working from my iPad this morning, so I'm going to improvise, which is always great to do on a Monday morning. I hope you guys had a nice weekend after the midterm. How does everyone feel after the midterm? That's the response I was looking for. I will try to release the marks later today if possible. I need to check a few things in there. I'll either do it today or if not, then tomorrow. Okay, so we are now moving on to the last section of the course, which deals with something called discrete mathematics. So up until now, pretty much everything we've done has been focused on continuum mathematics. So things like our systems of ordinary differential equations, those are continuous. Things like when we were looking at differentiation and volumes, so when we're doing our integration, those were also continuous as well. So lots of stuff that we've done so far has been continuous, but there's a big branch of mathematical biology that deals with things that are discrete. So what do we mean by that? Well, for example, if we are counting things, we're going to be talking about counting today. That is a discrete thing. If we have a discrete number of things, a finite number of things that we want to count, this might be, say, if you are setting up an experiment and you have different treatments and different options, you want to work out how many different experiments there are, how many individuals maybe you need to recruit for those, for something like a clinical trial. Things like probability as well, if we're thinking about discrete events, you know, if you roll a dice or if you flip a coin, how many possible outcomes are there? We're also going to get into, in a couple of lectures' time, thinking about graphs and networks. So graphs and networks are used for lots of things, whether it's modeling disease transmission between individuals in a population, or constructing food webs and thinking about flow of energy between individuals within that food web. Also constructing pedigrees and phylogenies as well to think about ancestry. So discrete mathematics is quite a big area, and we're just going to try and touch on a few of those topics before the end of the course. Okay, so the pre-lecture went through the first sort of principles of counting and ideas about factorials as well. Introduced this idea that, okay, if we've got something like human insulin, which is made up of 2 peptides, and those peptides are chains of amino acids, we have different combinations of amino acids that form those peptides. So how many different combinations of things can we get? So the pre-lecture introduced you to the multiplication principle, where if you have these mutually exclusive independent events, we can just multiply the total number of outcomes of, say, event type 1 with event type 2, multiply those together, and that will give you the total number of outcomes that you can get. So if you roll a dice, a fair dice that has 6 sides, and we have a coin that can just be heads or tails, then there are 2 outcomes for the coin, 6 outcomes for the dice, multiply those together, 12 possible outcomes altogether. So the pre-lecture went through a couple of those examples, then went on to talk about permutations. So here we're thinking about ordering of things. So we care about the order. So in this case here, 1, 2, 3 is not the same as 3, 2, 1. Okay, we care about the order of these things. So in that case, all we need to do to work out the total number of permutations here is we take 3 factorial. So if we've got 3 elements, we take 3 factorial. If we've got n elements, we take n factorial. And what is factorial? Well, if we have n factorial, we just take n and multiply it by n minus 1, by n minus 2, by n minus 3, all the way down to 1. Okay, so all the numbers less than n will be integers. We also define that 0 factorial is equal to 1. So you don't need to worry too much about why that is the case, but if you do come across that 0 factorial, we're going to treat as 1. And then we went on to talk about these examples of jars with different colored balls in them. Mathematicians often like to talk about jars or urns with different colored balls in, and you're drawing them out. You can also think about like different colored socks in a drawer, and you're trying to get a particular combination or a particular set of socks that you're pulling out of that drawer, or in this case, balls out of a jar. The reason we think about these is because a lot of real-world problems can be distilled down to something of a similar nature here, where you're trying to think about combinations or permutations of things that you are drawing randomly from a set. So how do we work this out? Well, to work out the permutations, if we have n objects and we are drawing k things, where k is less than or equal to n, out of that set of objects, and we're not replacing them in. So that's key. We're not taking a ball out of this jar and then putting the ball back in. We're taking it out and placing it down, and taking the next one out and placing it down. A bit like if you ever see they do like draws for like the Football World Cup, where they put people into countries into different groups. You're not placing them back into that main pot. Okay, so how do we work this out? If we have n objects in our total set, and we were drawing k of those without repetition, we work out n factorial and divide it by n minus k factorial. Okay. So the kinds of questions that we can end up solving are things like, okay, how many 5-letter words with no repeated letters exist in the alphabet? And when we're talking about words here, we're taking basically just strings of letters as opposed to actual words in the dictionary. But you can work this out here by taking the number of letters in the alphabet, 26, which is our n. Our k here is 5. That's the number of things that we're withdrawing. And we work out then 26 factorial over 26 minus 5 factorial. And this gives us how many possible strings that we can end up with. Okay, so we're going to be going through some examples with permutations today, as well as multiplication principle. So let's jump in. This one. Okay, so first of all, to test the effects of a new drug, we're going to take part in a clinical trial, or we're going to set up a clinical trial. So we need to know how many possible outcomes and how many patients we need, things like that. So how do we do that? Well, here we've said each patient receives either a new drug or an established drug or a placebo. So there are 3 possible treatments, if you like: new drug, old drug, or a placebo. And you want to enroll 50 patients. The question is then, how many ways can we assign them to these 3 treatments? Well, here we're not caring about permutations here, we just care about multiplication. So here we would apply the multiplication principle. So 3 treatment possibilities for each patient. Each patient is independent. So we take 3 to the power of 50. So we're multiplying 3 by itself 50 times, and those are all the possible outcomes that we could get. We could have this person here having the new drug, this person here having the old drug, this person here having the placebo. We could do that in different combinations, but there's 50 of them. So there are 3 possibilities for this person, 3 possibilities for this person, 3, and so on. So we just multiply all those things together. So 3 to the power of 50, which is a very, very, very big number. So I wouldn't expect you to calculate that kind of thing. Okay, so nice and simple multiplication principle. We would just say you have 3 to the power of 50 here. Okay, let's move on to another example. So methylation is something that happens to DNA, like methyl groups get added to DNA, and that can affect expression of different genes. And we can say, suppose there are 8 possible variants for a gene. We call these variants alleles. And we're further going to suppose that each allele can be methylated or not. So they have this methyl group attached to them or not. And we have these 8 variations of this gene. And then the expression level of a gene depends both on the actual allele that is there itself, one of those 8 things, as well as whether it has a methyl group attached to it or not, whether it's methylated. So considering both of those different things as being independent, how many possibilities are there for the level of this gene being expressed? Any ideas? Yeah. Yeah, it's as simple as that. We're just multiplying. There are 8 possible variations. This is like rolling a dice and flipping a coin. 8 possible variants of our gene. We have 2 possibilities in terms of methylation. It's methylated or it's not. We do that for every single one, just like if we were assigning treatments to different people. So we have total number of possibilities is just going to be 8 times by 2, 8 alleles, binary outcome, whether it's methylated or not. So we have 16 possibilities. Okay. I want you guys to have a go at working this one out. Don't actually work out what the final answer is in terms of like writing it down. You can write it out in a power form. here we've got telephone numbers in North America, and we're going to ignore the fact that we're going to use different area codes. We're interested in what are the total number of possible phone numbers that we could have. So there are 10 digits, and out of those 10 digits, the first two, they can't be 0 or 1, but all of the others can be anything through from 0 to 9. Okay, so have a chat with your neighbor while I try and figure out if I can get my screen sharing working again. Have a chat with your neighbor, see if you can figure out how many different telephone numbers there could be in North America. The first two can't be 0 or 1. Sorry? The first digit can't be 0 or 1. So the first digit can't be 0 or 1. The rest of the digits can be anything. Okay. No, I need a Apple Pencil, and for some reason everything was working fine before I came in and has now failed. So great. Okay. I've made some progress, but something else has died in the meantime. So great start to the week. Okay, how many telephone numbers can we have in North America? Right, I'm just going to switch back to this because it's useless. Okay, so we have 10 digits, but the first, so for most of those digits, we're told 9 of them we can have any possible digit. So there are 10 options for each of those 9. So we just take 10 times 10 times 10 times 10 times 10, and so on, 9 times. So we're going to have 10 to the power of 9. And the first digit, we can't have a 0 or 1. So in that case, we have to have 8. So we have 8 times 10 to the 9. So if I was to ask you a question like this in an exam, say, I wouldn't expect you to write down 8 with 9 zeros after it, okay? Or if it was something that was, for the example above, say, if you didn't have calculators, this might be an example where I give you guys calculators to work out things like this. If it was proofs to 50, I wouldn't expect you to write down what proofs to 50 is, okay? If it's a fairly low number, then it's fine. Likewise, the example of like letters and words in the alphabet, permutations of 26 to the 5, and more interested in your calculation and your final answer. So if you left it as 26 times 25 times 24 times 23 times 22, that would be okay. Okay, let's move on and think about another example here. Can I just have a quick show of hands? Who got the telephone number 1? Okay, you guys. Okay, we're now going to be thinking about what happens if we have a track team of sprinters. So there are 10 possible sprinters, and we're going to make different teams, relay teams from these sprinters, okay? So we have 4 individuals on a relay team, and we want to know how many different relay teams we can form. We're going to assume that every person can run in every position in the relay team, so we don't have any issues with people who can only start or who can only be on the final leg. And we want to know, like I say, how many teams can we form from these 4 how many teams of 4 can we form from these 10 sprinters? The key piece of information here, what I would typically do if I was able to actually write on my screen right now, would be to underline we have 10 sprinters. So 10 is key. 4 is the number of individuals we're going to have on a team. Other key pieces of information, each person can run in any position. Obviously, there's going to be no repetition because we're assuming that individuals can't run more than once. So what does this all amount to? What this amounts to is we need to find the number of ordered 4 subsets. So we have a set of 10, and we want a subset of size 4. And we care about the order of these things. So individual A starting, well, if we had individuals A, B, C, and D, that is a different relay team to DCBA, okay, because the order of those individuals has changed. Okay, so we care about the ordering, which means we care about permutations. So how do we work this out? Well, we had that formula, remember, P, N, and K, where P, N, and K is equal to N factorial over brackets N minus K factorial. So have a go at working that out. If you've got a calculator, you can work out the final answer in this case as well. I will go around and answer any questions you might have. Finally, yeah, it's only 25 minutes late. Okay. Right, so thankfully, it's going to die any second, I know, as soon as you start writing something. So like, what do we need here? The key piece of information, we have 10 sprinters. So we're withdrawing, this is like having 10 balls in a jar, and we're withdrawing those balls from the jar. That's why we often think about those balls in a jar situation. So we have 10 different colored balls in a jar, and we're withdrawing 4 of those, okay? And we're not placing any of them back, which is essentially the same as assuming that each person can run in any position. And as well, we're all, well, that's not quite true. We're assuming that each person can run in any position, so it doesn't matter if we pull them out first or third. That's a different ordering. And we're assuming that individuals can't run more than once. So it's kind of implicit into the fact that we're using relay teams here. So how many different teams can we form? Well, what do we need? We need to find the number of ordered 4 subsets. So when I say a 4 subset, all I'm saying is we have a set of individuals. There are 10 individuals here. A subset is just well, it's kind of what it says on the tin, right? Subset is a smaller grouping. It could actually be the same size. It's anything from that set itself, okay? So 4 subset, and this is a set of size 10. Again, like I said a few times in terms of like structuring your answers for questions, if this was on a homework assignment or if it's in an exam, it's good to write down like mathematically what you're actually trying to do here, okay? If I just jump straight in and write down P104 is equal to blah, blah, blah. Suppose I mistakenly wrote down P410. I got the order the wrong way around and I mucked up the formula, or I put the wrong numbers down by mistake. I started writing down 12s and 6s or whatever. You'd get 0 marks, okay? But if you write down something like this that I've got at the top, stating what you're actually trying to do, you'd get some partial marks for that, okay? So always good to write down what your intention is, because sometimes we make mistakes when we actually go and do the calculations. If you've got your intention there, then it's clear that you kind of understand what's going on, even if you screwed up the execution, okay? Okay, so P104, we have, our n is going to be 10 here, so we have 10 factorial on the top. And then on the bottom, we have n minus k factorial, so we have 10 minus 4 factorial. So this is 10 factorial over 6 factorial. And of course, you could work out 10 factorial, you could work out 6 factorial, and then divide the first by the second. But we can also take advantage here of thinking about some cancellation. So 10 factorial is just 10 times by 9 times by 8 times by 7 times by 6 factorial. And we have a 6 factorial on the bottom. So we can cancel these two things out. This should work out to be, I think, 5040 possible relay teams. Did anyone else get that answer? Yes. Well done, team. Okay. So these kinds of questions, I would say the difficult part is not so much the actual calculation bit itself, it's making sure that you write down the correct things, okay, that you're in the correct example. We're going to be getting onto other things next time called combinations, where we don't care about the order, whereas in permutations, we do care about the order. So making sure you're using the right formula to work out the right answer, okay, that you're choosing your n and your k correctly. It won't work in this case if your n and your k are the other way around, but you'd be surprised at how many interesting answers we get sometimes. Okay, let's think of another example here. The nice thing about these questions is they're quite short. The answers are nice and fairly short to work out. So dengue fever. So dengue fever is an infectious disease caused by a virus spread by mosquitoes. And dengue is really interesting because there are 4 different strains. If you get dengue the first time, most of the time, it tends to be fairly mild for that first infection, okay? And you can't be infected by the same strain more than once. What's really important for dengue is that the second infection, which can occur by many other strains, the second infection is often worse than the first infection. This is one of the reasons why we struggle with vaccines for dengue virus, because the second, when you vaccinate someone, it almost acts like a first infection, and the second infections are the worst thing. So one of the real challenges has been to try to develop vaccines that vaccinate against more than one strain, and so behave more like vaccinating following a second infection. So you get the immunity following a second infection, but you're not having the problems associated with that second infection, okay? But for the purposes of this question, we're just going to think about severity. In this case, the severity of the second infection, depending on the identity of both of those strains, okay? So the ordering of these strains will matter. So getting strain 1 and strain 2 will give you a different severity than getting strain 2 than strain 1. So we care about the order as well as the identity of those different strains. And we want to think about how many different levels of severity are possible for an individual acquiring a second infection. So that's a lot of words here, and distilling this down into the actual, what do we need to do mathematically is more of the challenge than actually working out the final answer, okay? So what are the key pieces of information here? Let's go through it again from the top. So I want someone to raise their hand when they think I've said a key piece of information. So dengue fever is an infectious disease caused by a virus. There are 4 main viral strains. Okay, key piece of information, 4 main viral strains. And an individual can never be infected by the same strain twice. Okay, good. What's that telling us then? In terms of the jars and the colored balls from the jars, what's the analogy here? So can't repeat. Okay, yes, that's like taking a ball out of the jar and saying, we're not putting that ball back in the jar because they're not being infected by the same strain again. Again, this is why we use those analogies of balls in jars, okay? Okay, however, a second infection can occur by any of the other strains. Okay, that's fine. We're assuming essentially there's no cross immunity. The severity of the second infection depends on the identity of both the strain that caused the first infection and the one that caused the second infection. So what's that telling you then? You raise your hand. Okay, so the order matters. Yeah, so we care then about permutations. We're not in a situation, we've not met combinations yet, but it's not a case of combinations that matter, it's permutations that matter. So depends on the identity of both strains. And we're talking as well as the order in which they're required. Okay, so how many different levels of severity are possible? We need to work out the number of ordered 2 subsets. Okay, so it's ordered because we're caring about the order in which you get these things, the permutations matter. 2 subsets because we're talking about the second infection, okay? So we're assuming that we're just interested in individuals that have had 2 infections, not 3 infections or 4 or 1. So we want 2 subsets of a set of size what? So we're getting 2 subsets from a set of size. Anyone? 4, yeah. The reason it's 4 is because there are 4 viral strains. So that's just like having 4 different colored balls in a jar, okay? So where do we work this out? This is going to be our permutations of what? What are the 2 numbers I put in here? 4 and 2. Okay, so what's that going to be? That's 4 factorial over 4 minus 2 factorial, which is 4 factorial over 2 factorial. So we could write this as 4 times by 3 times by 2 factorial over 2 factorial, which is 4 by 3, which is 12. So we have 12 levels of severity. So another tip as well when writing your answers, don't just leave this as 12. 12 for what? Okay, think about your communicating this back to someone. You've interpreted this biological problem mathematically. You've done your analysis on it to work out what the answer is, and then finish up by saying, what does that 12 actually mean? It's 12 levels of severity that are possible. Any questions on any of this so far? Or is it nice and simple? I think when I went to university and studied mathematics, my family thought I did counting. And technically we did for a little bit. I think they just thought I sat there doing like mental arithmetic for 4 years. Okay, let's do one more example here. Yeah, let's just do one more. Okay, so this example is actually in the textbook. So these are nonapeptides. Nonapeptides are peptides with 9 amino acids. That's where the nona comes from. Nona meaning 9. So there are lots of different types of peptides that we can get that have 9 amino acids. Okay, so there are 2 here. Oxytocin is one, vasopressin is another. There are other different ones that we can get. So both the actual amino acids that appear in here, as well as the order matters. Okay, so if we change the order of these things around, say switching these ones here and these ones here, we would get something different. Okay, it wouldn't be the same. It wouldn't be the same peptide. It would have a different biological or biomolecular function. Okay, so they contain 9 amino acids. So that's our first key piece of information there, right? 9 amino acids. We're told there are 20 different amino acids. So how many different nonapeptides are possible? What do we need to use to work this out? Let's have a show of hands. Do we need to use, who thinks we need to use the multiplication principle? Who thinks we need to use permutations? Who doesn't know? Okay, thank you for your honesty. Okay, so for this first part, we just need to use the multiplication principle. Why is that? Well, we're told there are 20 different amino acids, and we just want to know how many different nonapeptides are possible in principle. So that means in our first location, imagine we've got this string of 9 amino acids. In this first one, we can put 20 things. In this second one, we can also put 20 things as well. So here we're allowing repetition. We've not had a situation where we've said you use an amino acid once and you can't use that amino acid again. You could just have the string of exactly the same amino acid 9 times. Okay, so we do this 20 times 20 times 20 times 20. So this is just going to be 20 to the power of 9. So again, this is a huge number of possible nonapeptides that we can have because we have 20 amino acids. How about the second question then? Think about the second one. How many different nonapeptides are possible if no amino acid is ever repeated? Have a chat with your neighbor and see if you can figure out what that is. Okay, guys. This is the last question, so we can finish up after this and you're free to go. So how many nonapeptides are possible if no amino acid is ever repeated? So this non-repetition is important. So again, write down what you're going to do. So we are doing something without repetition. So we need the number of ordered 9 subsets. The reason we're doing 9 subsets here is because they're nonapeptides. There are 9 different amino acids of a set of size 20. So you notice with a lot of these permutation questions, it's basically the same thing, but just with different numbers. Okay, it's all about distilling what the question is actually trying to ask from you. That's the skill. So here you want, the reason we're not using the permutation, here we're not using the multiplication principle is because unlike the one above, rather than having 20 possibilities for the first amino acid and then 20 for the second and 20 for the third, here, once you've used 1, you only have 19 for the second and then 18 for the third and so on. So this is what we're working out in the second example. So here we want to do P of what? What are the numbers I put in here? Altogether, what's the first number? 20. Okay, and what's the second number? Okay, there we go, nice and easy. So what does that look like? So we have 20 factorial over 20 minus 9 factorial. Again, it might sound a bit laborious, but write out this intermediate step, especially on an exam when you're rushing. It's very easy to make a mistake here and actually accidentally write down, say, 20 minus 11. So something people would often do here is they'd write down 20 factorial over 9 factorial. Okay, if you do that, you might not get the marks. Okay, so write down the intermediate step. So 20 factorial over 11 factorial. In this case, that is a big number. Both of these things are big numbers. You could write this top thing out as 20 times 19 times by 18 and so on, all the way down to 12. That's quite a long string of things. So if it was in an exam as well, I would specify the kind of format that I would want you guys to put it in, okay? And we're finished early today. I'll hang around for a few minutes in case you guys have any questions, though. If not, I'll see you on Wednesday.